Welcome to the deep dive. We know you're someone who actively works to cut through the daily noise, bypassing the endless scroll of news feeds to find those genuine moments of insight that actually reframe how you see the world.
Right, and that is exactly the mission we're on today.
Exactly. It's late February 2026, and if you haven't been obsessively tracking the robotics industry over the last few quarters, you are in for a pretty profound recalibration of what you think is currently possible.
Oh, absolutely. I mean, we have officially crossed a threshold that most experts thought was still at least a decade away.
Yeah, we've transitioned from those agonizingly slow, highly speculative laboratory experiments. You know, the ones, the fragile machines tethered to ceilings that take like 3 minutes to carefully identify and pick up a single plastic block.
Right, the viral videos where they always end up falling over.
Yeah, exactly. We've moved from that to high fidelity, high speed industrial reality. So the goal of this session is to synthesize a truly massive stack of sources we've curated for you.
It's a huge stack. It really is. We're looking at dense technical papers on tendon-driven kinematics, aggressive market radar reports tracking global supply chains, raw dispatch videos straight from the crowded floors of CES 2026.
And even public relations wires dissecting the technological implications of the recent Chinese Spring Festival gala.
Right.
If we connect this to the bigger picture, the stakes become almost unfathomable.
They really do.
According to one of the major comprehensive market reports in our stack, we're looking at a projected market capitalization that could reach $910 billion by the year 2040.
910 billion.
Yeah. We have to completely discard the mental model of robots as neat lab tricks or viral marketing videos of machines stumbling over cardboard boxes.
It's way past that now.
The sources indicate we are now talking about scalable armies of humanoid robots stepping onto automotive factory floors, integrating seamlessly into highly sensitive aerospace manufacturing facilities.
And much sooner than most anticipate walking right into our homes to perform general domestic labor. The technological evolution has been so violent and rapid over the last 24 months that it requires a complete ground-up reframing of how we view embodied intelligence labor economics and manufacturing scale.
And that reframing brings us directly to the central theme we're going to be weaving through this entire discussion today. We're calling it the Great Robotic Divergence.
It's a great robotic divergence. I like that.
It's an intensely complex, multi-layered debate that's currently just tearing through corporate boardrooms, venture capital firms, and university research labs alike. The core question is really this: is the United States currently establishing an insurmountable lead in advanced artificial intelligence?
What we might classify as the brain of the robot.
Right, exactly, the brain. While China has already definitively and kind of quietly won the race on global robotics manufacturing.
The physical body.
The body, yeah. We're going to examine that divergence from every possible angle, from the molecular strength of synthetic tendons to the macroeconomics of global supply chains. But before we get into the weeds, I do need to make a mandatory structural check regarding our sources.
Yeah, that's important to clarify up front.
Several of the reports we're analyzing today touch heavily on ongoing geopolitical and trade tensions, specifically regarding U.S. versus China technological hegemony, semiconductor export controls, and supply chain dominance.
Right.
So we want to explicitly assure you, the listener, that we are not taking sides or endorsing any political stance here.
Not at all.
Our mandate is strictly to impartially report the raw data, the structural engineering breakthroughs, and the varying market perspectives contained within the source material. We're going to lay out the arguments and the evidence exactly as they appear in the documents so you can evaluate the landscape and form your own conclusions.
That is a vital distinction to establish right at the top, because the raw data and the engineering achievements we are about to explore are objectively staggering, regardless of your vantage point on international trade policy.
Totally.
I mean, the mechanical engineering alone, divorced from any economic context, is enough to challenge fundamental assumptions about material science and kinesthetic control.
So let's set a scene to ground exactly what kind of physical capabilities we're talking about here. I want to take you back just a few days to February 23rd, 2026.
Okay.
Picture the atmosphere of the CCTV Spring Festival Gala in China. Now, this is not a niche tech conference, right? This is a massive cultural touchstone broadcast to hundreds of millions of viewers simultaneously.
This is a huge deal.
Right there on the main stage, sharing the spotlight with human performers in a highly choreographed program titled Wu BOT, is a perfectly synchronized group of Unitree G1 humanoid robots.
And they were not just standing there waving at the crowd or doing basic rigid arm movement.
No, they were performing incredibly complex, high-impact martial arts routines. The source documentation details them executing 3-meter-high backflips, springing together 7.5 continuous breakdancing air flares, and sprinting across the stage at sustained speeds of 4 meters per second.
Which translates to roughly 14 kilometers per hour, by the way.
Yeah, 14 kilometers an hour. And they were executing these movements with a level of biomimetic fluidity that genuinely blurred the line between electromechanical actuation and human athleticism. Okay, let's unpack this. Why should an engineer or investor care about a television performance? Why are we analyzing a highly choreographed dance routine as a data point for industrial readiness?
It's a great question, because to an untrained observer, a stage routine looks like pure, heavily scripted entertainment. But to a roboticist or a control systems engineer, that specific stage performance served as a highly rigorous public validation of extreme high-speed joint coordination and dynamic balance recovery.
Right, it wasn't just a pre-programmed track they were on.
Exactly. According to the technical analysis papers we reviewed breaking down the event, this was absolutely not an ornamental display utilizing pre-programmed, rigid M-blind movement scripts.
Because the stage is a chaotic environment.
Yes. The gala stage is an unstructured, highly dynamic, and unpredictable physical environment. These robots were navigating that space fully autonomously. They were utilizing what is known as a dynamic force-position hybrid control system.
Which sounds complicated, but it's basically how they don't break when they land, right?
Precisely. To put the physics of this into perspective, the instantaneous mechanical torques required to launch a machine weighing roughly 35 kilograms over 3 meters into the air, control its rotational inertia mid-flight, and then have it land stably on 2 distinct points of contact without shattering its internal components.
It's immense.
The forces are simply immense. It requires a system capable of high-fidelity estimation of contact states in real time. It's adjusting motor output on a millisecond basis to account for the slight variations in the stage floor's friction and the robot's exact angle of descent.
And the detail in the report that really caught my attention wasn't even the successful backflips. It was a specific moment during the routine that included a pre-planned fall.
Oh yeah, that was incredible.
Right. One of the G1 units intentionally stumbled and completely collapsed onto the stage. But instead of the performance halting, or a team of technicians rushing out with laptops to manually reset the machine, the robot executed a perfect, fully autonomous balance recovery cycle.
It did it completely on its own.
It dynamically calculated its own spatial orientation, recognized it was on the ground, formulated a bespoke motion planning algorithm on the fly based on the exact position of its tangled limbs, and fluidly stood back up to rejoin the synchronization.
That demonstrates a level of systemic resilience and adaptability that we usually only associate with biological organisms.
Yeah, it looked like a person tripping and just getting back up.
And that autonomous recovery is the critical differentiator between a fragile laboratory prototype and a robust industrial machine. If a robot is going to be deployed in a chaotic factory or a cluttered home, it cannot require human intervention every time it experiences a kinetic disruption.
Right. You can't just throw an error code every time it bumps a table.
Exactly. But the significance of the Unitree G1 extends far beyond its athletic capabilities. The true disruption lies in the scale of their production pipeline, which brings us to the market data outlined in the recent reports we looked at.
Right. There was actually a pretty significant industry dispute recently regarding global shipment numbers.
The Omdia report.
Yeah, a prominent third-party market research firm, Omdia, released a report that initially placed a competing Chinese company, Agibot, at the #1 spot for global humanoid shipments in 2025. They estimated Agibot moved around 5,100 units.
And Unitree was not happy about that.
Not at all. Unitree immediately issued a formal clarification statement publicly correcting the research firm. Unitree officially stated that they shipped over 5,500 pure humanoid units in 2025.
And they were very careful to explicitly note that this 5,500 figure strictly isolates their bipedal humanoids. It completely excludes their highly successful lines of wheel logistics robots and quadruped robotic dogs.
Just the humanoids.
When an emerging industry is moving so fast that major market research firms are underestimating core production numbers by significant margins, it indicates a highly volatile and hyper-accelerated manufacturing environment.
And Unitree's stated production target for 2026. They're aiming to manufacture and ship a staggering 20,000 humanoid robots.
20,000 fully autonomous bipedal humanoids in a single calendar year.
To contextualize how massive that number is, we have to look at the broader global ecosystem. The market research data in our stack estimated that total global humanoid robot installations for the entirety of 2025 only reached roughly 16,000 units across all manufacturers worldwide.
So Unitree wants to beat the entire global 2025 output by themselves in 2026.
Exactly. If we take the slightly more conservative baseline estimate of 13,000 global shipments, the combination of Unitree and Agilbot alone captured over 70% of the entire global humanoid market share by the fourth quarter of 2025.
This dynamic is what the reports classify as the two-power rivalry dominating the Chinese domestic market. We are witnessing a ferocious neck-and-neck race in mass production scalability.
Agilbot is not sitting still either.
No, they just celebrated rolling their 5,000th embodied robot, designated the X2, off their automated assembly lines late last year.
This rapid aggressive scaling is decisively shifting the center of gravity for the global humanoid robot industry away from traditional tech hubs and squarely towards specialized industrial manufacturing clusters located in Chinese cities like Suzhou and Hangzhou.
And it is crucial to understand that these robotics companies, Unitree, Agilbot, and others, are not operating in an isolated vacuum. They are the beneficiaries of what our sources describe as a massive multi-layered proxy war occurring beneath the surface of the hardware market.
A proxy war.
Yes, the major Chinese internet and technology conglomerates, entities like Tencent, Alibaba, ByteDance, and Meituan, are currently pouring unprecedented amounts of venture capital into this specific hardware boom.
Right. The reports mention them funding newer hyper-aggressive startups like Variable Robot, which recently secured a massive 1 billion yuan Series A plus financing round, as well as companies like Zhejiang Dynamics.
The strategic imperative behind this capital flood is entirely about ecosystem preservation. These internet giants operate massive digital empires, e-commerce, food delivery, logistics, social media, cloud computing.
Right.
They recognize that the era of pure software dominance is plateauing, and they are desperate to secure their tickets to the embodied AI future.
But why rely on proxies? I mean, if Alibaba or Tencent want a robot, why don't they just build it themselves internally?
Because hardware is ruthlessly difficult, and their core competency is software and platform management. They realize that in the near future, possessing the smartest AI model in the world will yield diminishing returns if that intelligence lacks a physical, versatile body to interact with the material world.
Ah, I see. So for Meituan, a humanoid robot represents the ultimate last-mile delivery and logistics node.
Exactly.
Yeah.
For Alibaba, it represents the complete automation of unstructured warehouse picking and sorting. To Tencent, it could be the physical avatar of their digital WeChat ecosystem right within a user's home.
So these internet giants are essentially utilizing these heavily funded robotics startups as proxies to fight a proxy war for dominance in the emerging physical realm.
Yes, ensuring that whichever hardware platform ultimately reaches mass consumer adoption, their proprietary software ecosystems and AI models are the ones running the local operating systems.
That influx of massive institutional capital is effectively supercharging a structural advantage that China already possessed, which is a deeply entrenched, highly integrated manufacturing supply chain.
And this is exactly where we begin to see the profound market-distorting cost advantages emerge.
The sources are clear that Unitree's market dominance isn't solely attributable to clever balance algorithms. It is fundamentally rooted in their supply chain architecture.
They operate with an astonishing 90% self-research and manufacturing rate.
90%. Unlike many Western hardware startups that essentially act as system integrators, buying off-the-shelf premium components from specialized overseas suppliers and bolting them together, Unitree is manufacturing almost everything in-house.
Right. They are designing and machining their own harmonic reducers, which are the highly complex gears that give robotic joints their precision.
They're winding their own high-torque joint motors, fabricating their own LiDAR sensors, arrays their own proprietary motor drives, and their own main control system boards.
By vertically integrating the manufacturing process to this extreme degree, they have successfully driven their mass production costs down by an estimated 75% compared to the baseline manufacturing costs of their Western counterparts.
75% cheaper to build. The resulting retail price difference is the data point that completely recontextualizes this entire industry for me. The Unitree G1 humanoid, the machine capable of autonomous balance recovery and 3-meter backflips, is currently priced at approximately $13,500.
13,500. Just let the economics of that sink in.
Yeah, compare that figure to a legacy platform like Boston Dynamics' famous quadruped robot Spot, which has traditionally commanded a price point upwards of $74,500. And that's for a robot without highly dexterous hands.
We are looking at a highly capable, autonomous, bipedal humanoid robot equipped with advanced force control sensors that retails for less than the cost of a heavily used economy car.
When the unit economics drop to that level, the entire global conversation shifts permanently, from discussing experimental laboratory equipment to strategizing the deployment of a scalable, expendable industrial workforce.
It fundamentally alters the return on investment calculus for any logistics or manufacturing firm globally.
Oh,
However, this perfectly sets the stage to examine the other side of the great robotic divergence.
right, the U.S. side.
If we accept the premise presented in the sources that China is rapidly scaling the physical body at an astonishing rate, leveraging deeply vertically integrated supply chains and ultra-low manufacturing costs, we must simultaneously look at how the United States is relentlessly pioneering the cognitive architecture,
The brain.
the brain.
But a highly capable mass-produced body is ultimately a paperweight if it doesn't possess the cognitive architecture to navigate a dynamic, unpredictable environment.
Exactly.
That's the specific moat the U.S. is trying to dig. If you're constructing a robot intended for general-purpose labor, the hardware is useless if the system doesn't know how to interpret its surroundings and execute complex, multi-step tasks without hand-holding.
The United States is laser-focused on advanced cognition, and when we look at the 2025 top 10 humanoids list provided in our stack, it is heavily dominated by U.S.-based heavy hitters that are aggressively pushing the absolute theoretical limits of artificial intelligence.
Let's spend some time breaking down the capabilities of the major players driving this cognitive leap.
The first entity we have to examine is Tesla and their Optimus platform, specifically the Gen 3 iteration. Tesla occupies a unique space because they are attempting to bridge the gap between high-end AI and mass manufacturability.
They've publicly stated they're targeting a highly disruptive sub-$30,000 price tag for the Optimus.
Right, but the focus in the recent literature is on their cognitive and kinesthetic integration. The Gen 3 features highly complex hands with 22 degrees of freedom.
To give that some context, 22 degrees of freedom means the hand has 22 independent axes of motion, which begins to closely mirror the biomechanical complexity of a human hand. It allows for incredibly nuanced manipulation of tools and fragile objects.
Precisely. But the hardware is secondary to the software driving it. In late 2025, Tesla released demonstrations of the Optimus autonomously navigating a kitchen, recognizing ingredients and cooking full meals, as well as performing generalized household cleaning.
And the critical factor here is that this was achieved using end-to-end AI. There was no hard-coded programming dictating exactly how many centimeters to move its arm to grasp a specific spatula.
No, the system utilizes neural networks that learn purely from vast amounts of visual observation and kinesthetic data, effectively translating visual inputs directly into motor control outputs.
It just watches and learns.
Yes. Next, the sources highlight Figure O2, developed by Figure AI. This platform is notable for its rapid integration into heavy industry.
The documentation indicates that Figure O2 units are currently deployed working grueling 10-hour autonomous shifts at BMW automotive manufacturing facilities.
Their approach heavily relies on multimodal AI architectures. The robot doesn't just rely on cameras, it simultaneously fuses high-definition vision, advanced natural language processing, and highly sensitive tactile feedback from its end effectors to perform complex quality control checks and dynamic material handling on a live, chaotic factory floor.
It can theoretically listen to a human worker say, this panel feels misaligned, process the language, look at the panel, physically touch the seam to verify the tactile anomaly, and take corrective action.
It's incredible.
And we absolutely cannot discuss the U.S. landscape without detailing the evolution of Boston Dynamics.
Oh, yeah.
For years, they were famous for their hydraulic Atlas robot, the one that looked like a bulky linebacker doing parkour. But the sources highlight their complete pivot to a fully electric version of Atlas.
This new iteration utilizes what are called large behavior models, or LBMs, to achieve an astonishing 30 Hz full body control loop via advanced reinforcement learning.
We should unpack what a 30 hertz control loop actually signifies in the physical world because it is central to their cognitive advantage.
Mm.
Human reaction time to visual stimuli is generally around 250 milliseconds.
Right.
A 30 hertz control loop means the Atlas robot's internal AI is constantly ingesting sensory data, analyzing its entire physical state, recalculating the necessary physics, and sending fresh adjusted motor commands to every single joint in its body 30 times every single second.
That is roughly one full systemic reevaluation every 33 milliseconds.
It provides the robot with superhuman physical microcorrection capabilities, allowing it to maintain perfect dynamic balance and adapt to sudden environmental changes faster than humanly possible.
But to truly understand how the U.S. ecosystem is facilitating this rapid cognitive acceleration across all these different companies, we have to look beneath the robotic platforms themselves and examine the silicon foundation.
And according to the market reports in our materials, that entire foundation is almost singularly being architected by NVIDIA.
NVIDIA. We often think of NVIDIA simply as the company that designs the GPUs powering ChatGPT or high-end gaming computers.
Right.
But the documents indicate they are actively constructing the entire end-to-end foundational ecosystem for what they term physical AI.
NVIDIA's strategy is comprehensive. On the hardware side, in the first half of 2025, they launched the Jetson Thor computing platform. This is a system on a chip designed specifically from the ground up to act as the localized brain inside humanoid robots.
It is capable of an astonishing 275 TOPS, which stands for trillion operations per second.
275 trillion operations every second.
When a robot is processing complex computer vision natural language and that 30 hertz kinesthetic control loop simultaneously, it requires massive onboard compute that draws very little power, and Jetson Thor provides that exact architecture.
But as the sources emphasize, the hardware chip is only half of NVIDIA's moat. The software ecosystem is arguably more critical. They have launched Project GR00T, which is essentially a foundational general-purpose AI model designed specifically for humanoid movement and interaction.
Furthermore, they have developed highly sophisticated simulation platforms like Isaac Sim Omniverse and Osmo, which are fundamentally revolutionizing the methodology of how robots are trained.
The mechanics of how they utilize these simulation platforms completely flips traditional robotics training on its head. I want to spend some time here because this is where the U.S. cognitive advantage is truly generated.
That's fascinating.
In the past, if you wanted to teach a robot how to walk or how to pick up a mug, you had to physically code the movements, test it on a physical prototype in a lab, watch it fail, tweak the code, and try again.
And that real-world training methodology is inherently flawed because it is agonizingly slow, prohibitively expensive, and physically dangerous to the hardware.
Right.
If a research robot attempts a new task, loses its balance, falls, and shatters a proprietary $10,000 robotic arm during a training session, that represents a massive financial and temporal setback for the engineering team.
What NVIDIA's Omniverse and Isaac Sim platforms provide is a solution to the physical bottleneck. These are not simple video games. They are incredibly high-fidelity, physically accurate 3D virtual environments.
The physics engine perfectly simulates gravity, material density, friction coefficients, and even the exact weight distribution of the specific robot model being trained.
A developer can spin up and instance place 10,000 virtual replicas of their robot in 10,000 slightly different virtual kitchens and task them all with learning how to fold a specific type of fabric or navigate a cluttered space.
And because it's happening in software, they can accelerate time.
Yes.
These virtual robots use deep reinforcement learning to attempt the task millions of times in parallel, failing constantly but learning from every single failure without ever risking a single piece of physical hardware.
An AI model can effectively experience 10,000 lifetimes of physical trial and error in a single afternoon of server compute time.
Once the neural network has completely mastered the task and optimized the exact sequence of joint rotations required in the simulation, that fully trained brain is simply downloaded into the physical robot waiting in the real world.
This process is known in the industry as sim-to-real transfer, and it accelerates the learning curve of physical robotics exponentially.
And the ultimate destination of all this massively parallel simulation training, the holy grail that the entire U.S. tech sector is aggressively chasing, is the realization of AGI, artificial general intelligence, specifically manifested in the physical world through what are called VLA, or vision language action models.
The technical documents emphasize that the U.S. currently maintains a significant lead in achieving what is known as zero-shot generalization.
Zero-shot generalization is the concept that truly separates a robot from a machine.
Let's ground this with a practical example. Imagine you bring a newly purchased humanoid robot into your home and your kitchen is a chaotic mess.
Like after a dinner party.
Right. It's an environment the robot has never encountered before. There are dirty plates stacked haphazardly, a spilled glass of water pooling near an electrical outlet, and various pieces of trash scattered across the counter.
If this robot relied on traditional task-specific programming, you would have to preload it with a highly detailed 3D map of your specific kitchen and write a specific script detailing exactly how to clean that exact type of water spill.
It would be useless.
Completely useless.
But with a highly advanced VLA model capable of zero-shot generalization, the process is entirely autonomous. The robot uses its optical sensors to scan the scene that is the vision component.
It processes your casual verbal command, hey, please clean up this kitchen, understanding the intent and context that is the language component.
And then, crucially, it utilizes its foundational AI model to autonomously reason through the physics and geometry of the environment, formulating a completely novel sequence of movements required to grab a sponge, wipe the counter, avoiding the outlet, and safely load the plates into the dishwasher that is the action component.
That specific capability, the capacity for spontaneous autonomous reasoning in novel environments, is the true high-margin differentiator.
Historically, the predominant approach in robotics has been highly specialized task-specific training, which requires compiling massive bespoke data sets for every single specific operational scenario.
But real-world environments, whether it's the chaotic floor of a logistics hub or the infinite variables of a domestic living room, are entirely unpredictable.
The ability to generalize, to take fundamental physical and logical knowledge learned in one specific context and flawlessly apply it to a completely novel, unseen situation without requiring human intervention or reprogramming, is the precise threshold that separates a highly specialized industrial tool from a true general-purpose worker.
And the major U.S. players, leveraging the massive compute clusters and simulation architectures built by NVIDIA, are aggressively pushing the boundaries of this specific cognitive frontier.
Which brings us perfectly to the core underlying friction of our entire deep dive today. We are looking at the great robotic divergence.
Here is the debate.
I keep looking at these incredible manufacturing numbers coming out of China, the 20,000 production targets and the $13,500 price points, and I have to say I'm just not convinced the metal matters as much as the code.
Really?
Yeah, if I'm looking at this landscape objectively, I have to argue that software is the ultimate inescapable bottleneck in this entire industry. A cheap $13,500 robot body manufactured with perfect vertical integration is undeniably an incredible feat of modern mechanical engineering. But it is fundamentally practically useless if it does not possess the advanced VLA models required to understand and interact with its environment dynamically.
Okay, I see where you're going.
If it cannot achieve that high-level zero-shot generalization, it is ultimately just a very sophisticated remote-controlled toy, or at best, a rigid, fixed automation machine limited to highly structured environments.
Right.
The United States' relentless, heavily capitalized focus on AGI and cognitive flexibility is what will ultimately allow them to capture the absolute highest value tier of the global market.
Software immersion.
Exactly. In the long run, the real exponential profit isn't in selling the metal chassis, the synthetic tendons, or the motors. It is in licensing the intelligence, selling the ongoing software subscriptions, and monetizing the autonomous capabilities. The cognitive brain dictates the overall value of the platform.
That is the dominant thesis in Silicon Valley. And while it is true that the software represents the highest margin layer of the technology stack, I think there is a severe limitation to that perspective when dealing with embodied AI.
Okay, let's hear it.
You simply cannot divorce the software from the physical world. I will strongly advocate for the strategic dominance of the body. What's fascinating here is that my core argument, which is heavily supported by the deployment data in our sources, is that massive physical deployment is what actually drives the underlying AI data flywheel.
The physical deployment drives the software.
Yes, artificial intelligence models, no matter how sophisticated the underlying architecture, are ultimately only as capable as the volume and quality of the data they were trained on.
Sure.
Because Chinese manufacturers are aggressively deploying thousands of these robots like the Unitree G1 and the Agibot X2 into real-world, highly complex factories and logistics centers Right now, their control algorithms are constantly ingesting and learning from real-world edge cases.
But doesn't NVIDIA's Omniverse solve that? They can simulate millions of edge cases in an afternoon without needing the physical robots.
Simulations are incredibly powerful, but they are inherently imperfect approximations of reality.
Okay.
A simulation cannot perfectly replicate the unpredictable microvariations in tactile friction when a robot grasps a slightly defective out-of-spec component on a real assembly line, or the exact dynamic lighting changes in a dusty warehouse.
Oh, that makes sense.
When you have a fleet of 500,000 physical robots actively deployed globally, continuously sending back real-time, highly granular physical interaction data, your model iteration speed becomes statistically unbeatable.
The hardware acts as the sensory nodes?
Exactly.
Yeah.
The physical hardware acts as millions of sensory nodes feeding the central AI. Furthermore, the foundational premise that the U.S. will maintain an unassailable lead in AI software is being aggressively challenged. The software moats are shrinking much faster than anticipated.
Okay, we need to explore that claim deeply. When you say the software moats are shrinking, are you suggesting that the billions of dollars the U.S. tech sector is pouring into proprietary VLA models might not guarantee long-term market dominance?
Exactly. The market report we analyzed explicitly highlights a phenomenon they refer to as the DeepSeek effect.
The DeepSeek effect.
Earlier in 2025, the sudden, highly disruptive emergence of the Chinese AI model, DeepSeek, fundamentally altered the landscape. It empirically proved that Chinese software engineering capabilities can rapidly catch up to, and in several specific benchmarks, directly rival the massive, heavily funded U.S. AI giants.
Right, they did it with way less compute.
But more importantly, they demonstrated the ability to do so with profound, unprecedented cost efficiency, utilizing vastly fewer compute resources.
So the moat is shallow.
If the global open source community or highly efficient Chinese tech conglomerates can rapidly replicate reverse engineer or closely match the cognitive capabilities of the VLA models currently being developed in the US, then that vaunted intelligence advantage rapidly becomes commoditized.
And if the brain becomes a widely available standardized commodity, the economic dynamics dictate that the winner-takes-all scenario shifts entirely back to whoever controls the massive hardware manufacturing base and the physical supply chain.
Which is China.
That completely flips the venture capital thesis on its head for companies pouring billions into proprietary AI. If the intelligence becomes cheap and ubiquitous, the bottleneck reverts to the physical metal.
Exactly.
But I'll counter with the reality of the global hardware supply chain, which isn't as clean as just US versus China. Even if the US manages to maintain the absolute best, highly proprietary cognitive brain, physically constructing the body at scale is brutally difficult.
It is.
The reports specifically note that in order to realistically hit their highly ambitious $20,000 consumer price target for the Optimus robot, even a vertically integrated giant like Tesla might eventually be forced by sheer economic gravity to adopt Chinese suppliers for critical core components, specifically things like harmonic reducers and high-precision servo motors.
That is the exact friction point. Because the Chinese domestic integrated supply chain has been ruthlessly optimized over the last decade, they can produce these highly complex precision mechanical parts at roughly 50% lower costs than any available international alternatives.
Half the price.
The global hardware supply chain for robotics is incredibly fragmented and highly specialized. Attempting to completely bypass the established Chinese manufacturing ecosystem in order to build a purely Western robot might make commercialization at scale economically unviable for U.S. firms. They would simply be priced out of the market.
It is a profound and incredibly complex entanglement. You have U.S. companies possessing vastly superior cognitive architectures, potentially finding themselves entirely reliant on Chinese manufacturing infrastructure to achieve consumer scale.
And simultaneously, Chinese companies possessing unparalleled manufacturing scale and cost advantages are rapidly iterating their own AI models to aggressively close the cognitive gap.
The dividing lines of the Great Robotic Divergence are blurring rapidly in real time. So we want to pose a theoretical question directly to you listening to this analysis right now.
Think about this.
Think about the specific industry you work in or the business you operate. If you were forced to choose today, what matters more to your ultimate bottom line? Having exclusive access to the absolute smartest, most cutting-edge, generalizable software intelligence, or having immediate access to the most affordable, physically robust, and highly scalable hardware workforce that you can deploy by the thousands right now?
It is the ultimate brain versus body dilemma.
It really is, and how the global market answers that question will likely define the entire economic trajectory of the next decade.
And to truly appreciate the sheer complexity of the body side of that equation, we have to look much deeper under the hood.
Yeah, let's get into the engineering.
The astonishing physical agility we discussed earlier, the Unitree G1 executing 3-meter high backflips and recovering from falls, is absolutely not achieved using the traditional mechanical design paradigms that have governed robotics for the last 40 years.
It requires a fundamental ground-up shift in mechanical transmission architecture. Here's where it gets really interesting.
Oh yeah.
The mechanics of how they actually pull this off completely flips traditional robotics on its head. Let's transition into the raw mechanical engineering. How exactly do these heavy metal and plastic machines move with such fluid biomimetic grace?
The answer provided in our technical papers lies in a specific engineering architecture called TDT, or tendon-driven transmission.
I want to break down exactly how this works because it represents a massive evolutionary leap in hardware design.
To understand the innovation of TDT, we first have to understand the limitations of traditional robotic arms, which predominantly utilize rigid gears and direct drive motors.
Think of a standard, massive industrial robotic arm spot painting a chassis on a traditional car assembly line.
In that design, the heavy, dense electric motor responsible for movement is placed directly at the joint it is intended to actuate. The motor that bends the elbow is located directly inside the elbow joint. The motor that rotates the wrist is located directly inside the wrist.
This direct drive architecture makes the arm incredibly stiff, structurally rigid, and capable of extreme micromillimeter precision.
However, it also makes the arm incredibly heavy, bulky, and inherently dangerous to operate in close proximity to human workers.
Right.
Tendon-driven transmission, or TDT, completely discards this architecture in favor of an extrinsic actuation method. It heavily borrows principles directly from biological biomimicry.
Right. If you look at human anatomy, the powerful muscles that control the intricate movements of your fingers are not actually located in your fingers or even your hand. They are located further up in your forearm, and the mechanical force is connected to your fingertips by a complex network of biological tendons.
Exactly. TDT replicates this exact biological efficiency. It deliberately relocates the heavy, dense electric motors entirely away from the distal moving joints.
Instead of putting a motor in the wrist, the engineers hide the motors deep within the robot's proximal central structure, securely inside the main chest cavity, or eye up in the shoulder assembly.
The mechanical rotational power generated by those hidden motors is then transmitted down the length of the arm to the distal links, the wrists, and the individual finger joints through highly flexible, incredibly strong synthetic cables or tendons.
And the why behind this massive engineering shift is entirely focused on the physics of weight distribution and rotational inertia.
By intentionally stripping all of those heavy, rigid motors out of the arm's extremities, you drastically reduce the overall joint mass and, crucially, the rotational inertia of the limb.
When the Unitree G1 needs to violently swing its arms to generate the momentum required to run at 4 meters per second or execute a backflip, it is no longer fighting the physics of swinging a dense 10-pound metal motor located at the end of a long lever.
Instead, it is essentially swinging a highly lightweight hollow carbon fiber or plastic shell guided by internal wires.
This massive reduction in inertia allows for lightning-fast, highly explosive accelerations.
And beyond the athletic capabilities, it solves a massive industrial problem. It makes the robot exponentially safer to operate in dynamic environments around fragile human workers.
Right. If a highly compliant, low-inertia TDT arm accidentally swings and bumps into a human on a factory floor, it carries significantly less kinetic energy and blunt force behind it than a heavily motorized direct drive arm swinging at the same velocity.
It provides the system with inherent physical compliance, allowing the arm to yield slightly upon unexpected impact.
Which is huge for safety.
However, physically routing dozens of individual tension tendons through a highly complex, multi-jointed robotic body, threading them through a shoulder down past an elbow and into a wrist, introduces massive, almost prohibitive mathematical and mechanical engineering challenges.
Because of the friction.
The primary historic drawback of utilizing TDT systems is the introduction of massive internal friction and nonlinear material elasticity.
Whenever a tensioned tendon physically slides over a routing surface or wraps around an internal pulley to change direction inside the robot's arm, the overall tension distribution along that cable is rigidly governed by a principle of physics known as the capstan effect.
The mathematical reality of the capstan effect is fascinating.
The best way I visualize the capstan effect without getting completely bogged down in the advanced calculus is thinking about a practical scenario. Imagine you are trying to hold back a massive, highly aggressive dog that is pulling forward on a leash with all its strength.
Okay, yeah.
If you simply hold the end of the leash tightly in your bare hands, the kinetic force of the dog might easily overpower your grip strength and the leash slips.
Right.
But if you take that exact same leash and wrap it just one single time around the rough bark of a thick tree trunk, suddenly the physics completely change.
Yes.
You can now hold back that massive pulling force with almost zero physical effort using just 2 fingers. The internal friction generated between the rope and the surface of the tree grows exponentially with the angle of curvature.
That exponential multiplication of friction is the capstan effect in action.
In the technical papers we're analyzing, it is represented by the capstan equation, which states that the output tension is equal to the input tension multiplied by Euler's number raised to the power of the friction coefficient multiplied by the total cumulative angle of curvature.
That is a highly accurate practical analogy. Now take that exact exponential friction math and apply it to the internal workings of a humanoid robot.
The heavy motor located in the chest pulls the internal tendon that generates your input tension.
But before that physical pulling force can actually reach the fingertip to close the hand, the tendon must physically wrap around the complex internal geometry of the shoulder joint, slide past the internal routing of the elbow joint, and weave through the tight confines of the wrist.
And because of the exponential mathematics of the capstan effect, a highly significant percentage of the motor's initial pulling force is completely lost.
Lost absorbed as friction against the internal routing surfaces and pulleys inside the arm.
This inherent friction causes a massive loss of tension transfer, leading to severe operational dead zones, mechanical hysteresis, and a fundamental lack of precise kinesthetic control.
So practically speaking, if the robot's internal computer commands the finger to pinch a fragile object with exactly 1 newton of precise force, the motor pulls with 1 newton. But because of all that internal friction along the route, the finger might only actually pinch with 0.5 newtons of force.
Or it might release its grip milliseconds too slowly.
Precisely. And in older, early generation TDT systems, there was an additional highly problematic mechanical issue known as kinematic coupling.
What's that?
Because multiple tendons are routed through the same central joints, moving one joint would often inadvertently affect the tension on another.
Oh, I see.
For instance, if the robot needed to raise its shoulder, the physical act of the shoulder joint bending would inadvertently pull on the tendons that were routed through the shoulder on their way down to the wrist.
This would cause the robot's wrist to twitch or clench completely unintentionally every time it moved its arm, making delicate, precise manipulation impossible.
Exactly.
But the robots we're analyzing in these 2026 reports are absolutely not twitching or crushing fragile objects. They are executing flawless martial arts routines and autonomously folding delicate laundry.
So how did the mechanical engineers actually solve these seemingly insurmountable laws of physics?
Yeah, how did they fix it?
The breakthrough detailed in the papers is twofold, combining highly advanced mechanical architecture with complex computational software.
Okay.
Mechanically, engineers have developed and standardized what are referred to as FTTDH arms, which stands for fully decoupled, tendon-driven humanoid arms.
Fully decoupled.
They completely eliminated the issue of kinematic coupling by utilizing independent antagonistic tendon pairs for every single individual degree of freedom.
They've essentially engineered the internal routing to perfectly isolate the mechanical effects along the entire kinematic chain.
So physically rotating the shoulder joint no longer exerts any unintended parasitic tension on the tendons controlling the wrist or the fingers.
That solves the twitching, but what about the massive loss of force due to the capstan effect, friction?
That is where the computational software takes over. They solve the friction problem dynamically using highly advanced sliding mode control algorithms equipped with mathematical boundary layers.
Whoa, hold on a second. Sliding mode control with boundary layers. That sounds like graduate level control theory. Give me a practical analogy for what the robot's cognitive brain is actually doing there to manage the friction.
Think of it as a highly predictive, instantaneous microstutter correction system. The robot's internal processor is not just sending a blind command to the motor, it is constantly calculating the exact capstan equation in real time, thousands of times a second.
It intimately knows the exact current angle of every single joint in its arm and the exact friction coefficient of the synthetic tendons.
The algorithm actively predicts exactly how much mechanical force is going to be lost to friction at that specific microsecond across every specific angle of every single joint.
And then it just compensates.
The system intentionally overcompensates at the motor level, pulling slightly harder than necessary, precisely calibrated to ensure that once the friction absorbs its mathematical toll along the route, the exact perfect desired force is what finally reaches the fingertip.
And the boundary layer.
The boundary layer acts as a mathematical cushion. It prevents the motor from violently overcorrecting or chattering back and forth when it hits the target friction compensation value, ensuring the movement remains perfectly smooth and fluid.
It's an absolutely brilliant synthesis of disciplines. The AI software is constantly violently fighting the physical laws of friction in real time, executing thousands of microcalculations a second just to make the physical movement of the arm look completely effortless and natural to the human eye.
It really is.
And speaking of the precise movements of the fingers, let's dive into the absolute bleeding edge of this specific mechanical technology. I want to look closely at what the industry calls the end effector problem.
The hands.
Historically, manufacturing highly dexterous humanoid hands has been a massive logistical and computational nightmare for robotics companies because human hands are inherently asymmetric. You have a distinct left hand and a distinct right hand.
In a manufacturing context, that asymmetry means a robotics company is forced to maintain double the physical inventory. For spare parts, operate completely separate assembly lines for left and right units, and program vastly distinct kinematic mathematical models for the left and right sides of the robot's brain.
It introduces an incredible degree of inefficiency into the mass production pipeline, which drives up the baseline cost. But the source materials highlight a massive breakthrough that occurred on February 26, 2026.
Changingtek Robotics.
Yes, a specialized firm called Changingtek Robotics officially launched a hardware solution that completely neutralizes this problem. They introduced the X2 hand.
It is aggressively positioned in the market as the world's first truly adaptive left-right dexterous hand, or LRD hand.
By heavily leveraging that highly sophisticated, fully decoupled, tendon-driven transmission architecture we just broke down, the X2 hand possesses the mechanical ability to autonomously reconfigure its own physical geometry, seamlessly shifting from a left-hand state to a right-hand state depending on where it is mounted.
The concept of a single uniform hardware unit that can autonomously adapt its physical configuration based purely on the structural geometry of where you attach it on the chassis or what the specific task dynamically requires is incredible.
And the raw performance specifications detailed for the X2 are wild. Despite being constructed from highly lightweight materials to rigidly maintain that low rotational inertia we established was so critical for fast movement, it somehow achieves a maximum raw gripping force of 50 newtons per entire hand and can isolate up to 10 newtons of highly specific fingertip force per individual digit.
But the most staggering statistic in the technical sheet is its precise force control accuracy.
Plus or minus 0.1 newtons.
The documentation states it is accurate to a margin of plus or minus 0.1 newtons. That means this single adaptive end effector possesses the sheer brute mechanical strength required to carry heavy, dense metal factory equipment across a warehouse, but simultaneously possesses the hyper-delicate, micro-tuned sensory precision required to pick up a highly fragile, thin-walled glass beaker in a chemistry laboratory without applying the microscopic excess force that would shatter it.
Which naturally raises a highly critical fundamental question regarding the physical constraints of the system. What exactly are these internal tendons physically manufactured from to simultaneously achieve that level of raw, tensile strength, extreme flexibility, and micromillimeter precision?
You absolutely cannot utilize traditional braided steel cables. Steel is far too mechanically stiff, incredibly difficult to route through tight radius internal pulleys without fraying, and highly prone to catastrophic metal fatigue and snapping over repeated bending cycles.
The true, often entirely unsung heroes enabling this entire physical AI revolution are advanced, highly specialized synthetic fibers.
The absolute efficacy and reliability of any advanced tendon-driven robotic system is fundamentally limited by the realities of material science. In the 2026 manufacturing landscape outlined in our sources, two highly specific synthetic materials have emerged as the dominant industry standards, with each offering vastly distinct mechanical trade-offs depending on the robot's intended use case.
Let's examine the Changingtek X2 dexterous hand first because its requirements are so specific. Because that hand demands that insane plus or minus zero point 0.1 Newton gripping accuracy to handle fragile objects, they cannot afford any mechanical variance in the tendon line.
According to the detailed material datasheet included in our research stack, Changingtek utilizes a specific synthetic material called Vectron.
Vectran is classified as a liquid crystal polymer, or LCP.
The absolutely critical mechanical property of Vectran that makes it ideal for precision robotics is that it exhibits virtually zero creep.
Creep is the engineering term for the slow, permanent physical elongation or stretching of a material when it is subjected to a continuous long-term mechanical load.
Imagine hanging a heavy metal weight from a thick rubber band. Initially it holds, but over several days the rubber band permanently stretches and deforms.
In a high-precision TDT robotic system, if your internal synthetic tendon physically stretches or elongates by even a fraction of a millimeter over months of use, your entire complex kinematic mathematical model is completely ruined.
The robot's internal computer calculates that it pulled the tendon exactly enough to close its hand entirely around the glass beaker. But because the physical tendon has slowly stretched over time, the physical hand remains slightly open, the grip fails, and the fragile glass beaker slips and shatters on the floor.
Vectron's extreme dimensional stability entirely prevents this permanent elongation, allowing the robotic system to maintain perfect mathematically repeatable precision over millions of actuation cycles.
Conversely, let's contrast that material profile with the specific engineering requirements of the Unitree G1 robot, the machine, executing the highly dynamic 3-meter backflips and recovering from high-impact falls.
The G1 requires a vastly different material profile. Dimensional stability is important, but absolute shock absorption and extreme tensile strength are paramount.
For these high-load, extreme kinetic stress applications, the undisputed industry-standard material is Dyneema.
Dyneema is chemically classified as an ultra-high molecular weight polyethylene, or UHMWPE.
Its absolute defining characteristic is its sheer, almost incomprehensible tensile strength. It is statistically 15 times stronger than high-grade structural steel on a direct weight-for-weight comparison basis.
Furthermore, it possesses vastly superior natural abrasion resistance compared to other synthetics.
When the 35-kilogram Unitree G1 robot lands a massive 3-meter backflip onto a hard stage surface, the instantaneous kinetic shock load transferred directly into its mechanical joints is massive.
In that microsecond of impact, the internal synthetic tendons are violently pulled taut while simultaneously sliding incredibly rapidly over the internal routing spacer discs and friction pulleys.
If they used a lesser material, the sheer kinetic friction and tension would sever the lines instantly. Dyneema is the highly specialized secret ingredient that provides the required tensile strength and abrasion resistance, preventing those critical tendons from snapping under the incredible dynamic forces generated by explosive athletic robotic movement.
It is genuinely amazing how all of these seemingly disparate disciplines and industries perfectly layer together to create this moment in time.
It really is.
You have the multi-billion-dollar bleeding-edge AI cognitive models being developed in Silicon Valley, running on massively powerful specialized silicon chips, architected by NVIDIA, executing graduate-level sliding mode mathematical friction algorithms, pulling on highly advanced liquid crystal polymers invented by specialized material scientists, all seamlessly assembled and mass-produced within a highly integrated, hyper-efficient Chinese manufacturing supply chain.
Ultimately resulting in a $13,500 physical machine that can simultaneously execute martial arts routines and carefully fold your delicate laundry.
The convergence is staggering. So what does this all mean for the macro landscape? Where is this entire technological trajectory practically heading in the near term?
The overarching trajectory detailed in the market reports is becoming aggressively clear and highly compressed.
As Unitree's CEO Wang Xingxing explicitly predicts in the provided documentation, within a maximum timeline of 5 years, we will witness these humanoid platforms transition completely from being highly specialized, sometimes purely ornamental technological demonstrators, to fully integrated, ubiquitous general-purpose workers.
The intense mechanical breakthroughs we've dissected today, the fully decoupled tendon arms, the highly precise adaptive hands, the extreme cost reductions, are entirely intended for immediate practical labor deployment, not laboratory research.
The literature strongly suggests we are looking at highly imminent large-scale deployments across heavy aerospace manufacturing, intelligent automotive assembly, generalized domestic spheres, and critically specialized senior care and medical assistance.
And the absolute key driver Accelerating this compressed 5-year timeline is the exponential nature of the data flywheel we discussed earlier.
Right, the data flywheel is the engine of this entire revolution. When you combine Unitree's proprietary unified large model that processes physical interactions with NVIDIA's massively parallel Omniverse simulation platforms, the cognitive learning curve ceases to be linear. It goes entirely vertical.
When you analyze the industry projections, anticipating upwards of 500,000 highly capable humanoid robots, soon being physically deployed globally, continuously, sending back real-time granular interaction data from complex factory floors, sterile hospitals, and highly unstructured domestic homes, the iteration speed of their collective AI brains will be unprecedented in human history.
Every single time one specific robot physically encounters and successfully learns how to manipulate a new, weirdly shaped, previously unseen object in a dark logistics warehouse in Berlin, every single other robot connected to that global network instantly simultaneously gains that exact physical skill and kinesthetic understanding.
The hive mind acceleration is exponential.
And as highly aggressive companies like Changingtek, Agibot, and Unitree continue to ruthlessly drive down the baseline manufacturing cost curves through massive economies of scale and total vertical integration of the supply chain, the highly capable humanoid robot will very likely become as economically accessible and ubiquitous as the modern personal computer or the smartphone.
The macroeconomic implications of having highly autonomous, general-purpose, physically capable labor, widely available for a baseline capital expenditure of $20,000 a unit, will fundamentally restructure global productivity metrics, supply chain logistics, and traditional labor economics.
And that profound economic restructuring is exactly why you listening to this analysis right now need to actively care about and track this specific technological divergence.
This technology is absolutely not a speculative concept sitting 20 years away in a research lab. It is actively scaling in manufacturing hubs right now.
It is going to demonstrably impact your daily life and your industry much sooner rather than later. It will directly impact the baseline cost of the consumer goods you purchase, because those goods will increasingly be manufactured, sorted, and transported by these exact robotic platforms.
It will fundamentally alter the dynamics of the global labor market across almost every physical sector.
And very soon it will impact your immediate personal life when that $20,000 machine is standing quietly in your living room, autonomously folding your laundry, safely navigating around your pets and preparing your dinner, using its advanced zero-shot generalization VLA model to figure out exactly how to clean your chaotic, messy kitchen without ever being explicitly programmed to do so.
We've managed to cover an immense amount of complex ground during this session. We initiated the discussion with the macro strategic concept of the Great Robotic Divergence, analyzing the intense multi-layered strategic battle where the United States is relentlessly pushing the absolute theoretical boundaries of AI cognition, zero-shot generalization, and advanced simulation, while China concurrently dominates the physical hardware scalability, extreme cost reduction, and massive physical world deployment.
We've ventured deep into the complex mathematics and biomimicry of tendon-driven transmission, understanding exactly how the exponential friction of the capstan effect is computationally overcome, using sliding mode algorithms to create fluid superhuman movement.
And we zoomed all the way down to the micromolecular level, examining how the dimensional stability of synthetic fibers like Vectran and the extreme tensile strength of Dyneema make these incredible physical feats a material reality.
It truly is a perfect, unprecedented synthesis of advanced software architecture, mechanical engineering, and material science. But before we officially wrap up this session, we want to leave you with one final, highly provocative structural concept to mull over, a concept pulled directly from the concluding pages of the market report that we haven't even had the opportunity to touch on yet.
Yes, the concept of ultimate systemic convergence. As embodied artificial intelligence rapidly evolves and scales, leading industry experts are currently foreseeing a massive, practically inevitable convergence between two massive global industries that have up until this exact moment largely operated in complete parallel isolation.
The autonomous vehicle industry, specifically self-driving cars, and the humanoid robotics industry.
When you truly strip it down to foundational architecture, both platforms require the exact same core technologies: advanced spatial perception, instantaneous real-time decision-making in highly unpredictable, chaotic environments, massive onboard compute, and highly complex vision-language action AI models.
What theoretically happens to the global tech ecosystem when the proprietary algorithmic architecture guiding your autonomous vehicle safely down a highway and the architecture guiding your household humanoid robot safely down your hallway completely merge into one unified system?
What happens to the market dynamics when traditional legacy automakers, entities that already possess massive global manufacturing infrastructure, deeply integrated supply chains, and heavily funded internal AI divisions, pivot their immense resources toward building shared foundational brains that simultaneously pilot both your personal transportation vehicle and your physical robotic workforce?
The historical lines of demarcation separating the automotive sector and the robotic sector are about to disappear entirely.
It is a genuinely wild, paradigm-shifting concept to try and visualize. Your car sitting in the driveway and your household robot standing in the kitchen, seamlessly sharing the exact same continuous consciousness, instantly transferring physical spatial knowledge and cognitive reasoning between navigating a complex highway interchange at high speeds and navigating the fragile environment of your living room.
Thank you so much for joining us on this exhaustive deep dive into the physical AI revolution and the mechanics of the great robotic divergence. Keep actively exploring these concepts, keep questioning the economic and societal trajectory of these rapidly scaling technologies, and we will catch you on the next deep dive.